In the previous video, we're able to discuss the Wronskian of functions. It's actually a certain concept that we can use here when we're trying to solve nth order non-homogeneous differential equation using the variation of parameters. In this case, we are using the idea of the Wronskian of functions. Now, of course, we have the general form for a nth order non-homogeneous differential equation in this manner. We can write it in this form. We have here, of course, you would expect to have a certain variable here and a sub n of x, any function of x here. We have here the nth order derivative of y with respect to x, plus you have a sub n minus 1 x. You have here the nth minus 1 order derivative of y with respect to x, plus dot dot dot, plus you will have here a sub 1 of x dy over dx plus a sub 0 of x and y equal to a certain function here, let's say f of x. Okay? We're going to use here f of x. We used g of x before, but what has been clear here is that this is not equal to 0, so that our differential equation is a non-homogeneous differential equation, because if it is, then of course it's a homogeneous differential equation in higher order, and we can use the solutions for the homogeneous higher order differential equation. So what would happen here is this. Of course, what we have learned previously, similarly for the concept of what do you call this one, the nth order homogeneous, we actually have the solution in the form of forming this in a differential operator d. Okay, so we're going to have here differential operator d. Okay, then later on we moved into the auxiliary equation. Okay, which is actually f of m, and then we're going to equate it to 0. This is actually the same process even if we have also a non-homogeneous differential equation, because this will yield later on a result of y sub c pertaining on whatever be the roots of our auxiliary equation, whether they are real, distinct, or repeated, or imaginary, repeated imaginary. So we have those forms. And we also discussed in the use of the y sub p particular solution, okay, if we have a non-homogeneous differential equation pertaining on this not being equal to 0, we have a table for trial particular solution, where in fact the solution of a non-homogeneous differential equation is expressed as y is equal to y sub c. Again, the form or general form, if we have this differential operator and auxiliary equation f of m plus your y sub p. And y sub p again may be referred into the trial particular solution depending on what is your f of x here or g of x in the previous instance. Now, we have to talk about the variation parameter here, where in a situation when we don't know the actual form of this, okay, or there might be some instances that we know what is our function, whether it's an exponential, trigonometric, quadratic, or just simply linear or constant, but we don't know the actual form for trial particular solution for y sub p. Okay, what we know is that this will have to pattern on the type of roots, right? But y sub p, we don't know the table, we forgot the table, and we will no longer use them. Hence, this is the process now. We're going to use the Wronskian of functions. Now here is the form. After your y sub c be identified as the solution, c sub 1 y sub 1 plus c sub 2 y sub 2 plus c sub 3 y sub 3 until now whatever the roots are, the number of roots, c sub n y sub n. And again, these have different 4 forms, right? It has different 4 forms, where if the roots of the auxiliary equation are distinct and real, repeated and real, imaginary, or repeated and imaginary, they will all of course form into this manner. What we have now is the use of these functions here, whatever these functions here, would be related to our y sub p. Take note, we don't know the table of trial particular solution, so that is actually the same y sub 1, but it will be paired with u sub 1, u sub 2, u sub 3, until the number of functions that you could have here, u sub n, y sub n. That would mean this form together with that form when added will resolve the will result to our solution intended for the nth order higher higher order non-homogeneous differential equation. The concern now is what would be the use. Okay, so what would be the use now? Now the u are actually just results, so let me write it here. Our u sub 1 is actually equivalent to the integral of our u sub 1 prime. You will be having, of course, du here, whatever that u there. Okay, so u sub prime, okay, sub 1, just for the sub 1 itself, would be equivalent to the ratio, okay, the ratio of your Ronchian of the functions of the first column over the total Ronskian of functions. At this time, this corresponds to the Ronskian of functions already identified in the previous video. W sub 1, W sub 2, and W sub n are also considered as Ronskian of functions, but there are tweaks on the equivalent matrices. Okay, so matrices. Of course, this is also true for u sub 2. It's the integral of u sub 2 prime du, where u sub 2 prime is again the ratio of the Ronskian sub 2 and the original Ronskian. So it works for all u sub n is with the integral of u sub n prime du, where u sub n prime is actually the ratio of w sub n over your w, which are actually Ronskian. That's why we have here the Ronskian of functions. Now, we know the Ronskian of functions to be the determinant of the functions. So what would be the functions we're using here? It's actually these functions here, y sub 1, y sub 2, y sub 3, y sub n. That would be the use of our Ronskian. Okay. Again, the y subs are actually are derived as well from the y sub c. So of course we would always start with our y sub c. Now, what would be our Ronskian sub 1, Ronskian sub 2, and Ronskian sub n? Let me use here Ronskian sub 1 first. Supposedly, the original Ronskian, as mentioned here, using these functions, will actually come up with a certain matrix y sub 1, y sub 2, y sub 3, right? Those are the functions of the y sub n. And you will have here n minus 1 rows. Meaning, the number, it would form like y sub 1 prime, y sub 2 prime, y sub 3 prime, so on and so forth. That is actually for our w itself. W alone. That's for the Ronskian of functions. And of course, so on and so forth until n minus 1 rows. But for w sub 1, okay, it would actually using the first column, all the entries here are 0 until your f of x, the original right-hand side here. Okay? That would be for your w sub 1, and the same components here will be indicated. If it's w sub 2, so that item here, the first column, will use the same column of your w, but the second column will not have 0, 0 until f of x, and the same columns for the rest, and still idea is Ronskian. That's how different the Ronskian for w sub 1, sub 2, and w sub n to the original Ronskian. Okay, so here, this is the idea of the variation parameter. Yes, it's a little bit complicated because we don't have the trial particular solution for our y sub p. We know that if it's constant, we are going to have y sub p is equal to a. If it's linear, y sub p is equal to ax plus b. We also have for exponential, trigonometric, quadratic, and the combinations of all, so on and so forth. That is the first method we have learned in solving the higher order non-homogeneous differential equation. But this time, what if we don't have all of this, or we are required to use the variation parameter? That would mean our y sub p would be related to our y sub c. After we have done solving y sub c, the same y subs will be used to construct our y sub p, but they are actually has factors of use. The u's are actually the integral of the u's primes, which are actually the ratio of Wronskian subs and the original Wronskian. The Wronskian is for the functions indicated here, but the subs are actually removing all entries of that column, the numbered column, second column here. If it's third, it's a third column here. If W sub 4 is the fourth column, by all zeros until the last entry is your f of x. It's easier for us to do this one because once you use the determinant, when you have zeros, it's easier to compute for the W subs. But the W would be the original one pertaining on the Wronskian of the functions itself, y subs until y sub n. And then later on, you're going to take the ratio of them to get the primes, integrate them to get the u's, and then multiply them to your y subs. And whatever would this be, add it to your y sub c for your solution. To illustrate this further, we have a lot of examples to be provided here in this playlist. So please stay tuned for those examples as we are solving higher order non-homogeneous differential equation using variation parameters with the idea of Wronskian of functions. Thank you very much for watching.